Section 9.1, Part 4. Lesson objectives. Interpret a confidence interval for a population mean, assuming that the population standard deviation is known. Understand the role of margin of error in constructing the confidence interval. This is the formula for constructing a 1 minus alpha times 100% confidence interval for the population mean. We have our lower bound, which is our point estimate, minus what's called the margin of error, and the upper bound is our point estimate plus the margin of error. In this video we're going to talk about how do we interpret a confidence interval. A 1 minus alpha times 100% confidence interval indicates that if we obtain many simple random samples of size n from a population whose mean mu is unknown, then approximately 1 minus alpha times 100% of the intervals will contain mu. For example, if we constructed a 99% confidence interval with a lower bound of 52 and an upper bound of 71, we would interpret the interval as follows. We are 99% confident that the true population mean, mu, is between 52 and 71. For example, a 95% level of confidence, alpha equal 0.05, implies that if 100 different confidence intervals were constructed, each based on a different sample from the same population, we would expect 95 of the intervals to contain the parameter and 5 not to contain the parameter. This is going to be our interpretation template. So whenever we have a confidence interval and we are asked to interpret that confidence interval, this is the template that we can use. We are, and then you state the level of confidence. That's either going to be a 90, 95, or 99%. Confident that the true population mean, you put the mean in terms of the problem, is between, you state the lower limit and state the upper limit and include units when necessary. Let's do an example. Our Facebook example. The following represents a random sample of the number of friends for 40 users of Facebook. Assume that the population standard deviation is 53. Interpret the 95% confidence interval for the mean number of friends for all users of Facebook. So if you recall, we did this in the previous video. Our confidence interval has a lower bound of 114.4 and an upper bound of 147.2. So if we were to interpret this confidence interval, we would say we are 95% confident that the true population mean number of friends on Facebook is between 114.4 and 147.2. Here's some things to keep in mind. The value of mu is a fixed number. It is either in the confidence interval or not. So it is incorrect to say there is a 90% probability that the actual mean is in the interval between 22.3 and 23.5. What is correct to say is if we take a large number of samples collected and a confidence interval is created for each sample, then approximately 90% of those intervals will contain mu. Let's look at this visually. The horizontal segment represents the 90% confidence interval for different samples of the same sample size. In the long run, 9 out of every 10 such intervals will contain mu. So we have our mu here. These are 10 different confidence intervals. The dots are our point estimates, x bar, and we can see from this one under predicted a little bit too much and did not catch mu. The rest of them did. Let's do our penny example. Interpret the 99% confidence interval for the population mean weight in grams of pennies minted after 1982. If you recall from our last video, this is our confidence interval. To interpret, we would say we are 99% confident that the true population mean weight of pennies minted after 1982 is between 2.452 and 2.477 grams. Lesson objective. The margin of error E in a 1 minus alpha times 100% confidence interval in which sigma is known is given by the formula E equals Z alpha divided by 2 times the standard error. and this is assuming that the population which the sample was drawn is normally distributed, or the sample size n is greater than or equal to 30. Here's a visual for the margin of error. Here's our x bar. So if we take x bar minus our margin of error, we get our lower limit. And if we take x bar plus our margin of error, we get our upper limit. The margin of error depends upon three factors. The level of confidence. As the level of confidence increases, the margin of error also increases. The sample size. As the size of the random sample increases, the margin of error decreases. And the population standard deviation. The more spread that there is in the population, the wider our confidence interval will be for a given level of confidence. Let's look at this visually. We can say we can be 90% confident that mu lies in between these two values. Now, if we were to change the level of confidence to a 95, how would that change this interval? Well, with a 95, we're more confident, but with that increased confidence, there's a trade-off. Our confidence interval got larger. So as you increase the confidence level, the margin of error will increase, which will result in a wider confidence interval. Construct a 90% confidence interval for the mean weight pennies minute after 1982. Comment on the effect that decreasing the level of confidence has on the margin of error. So if we're doing a 90%, our z alpha divided by 2 is 1.645. So if we compute our lower bound, we get 2.456. Our upper bound would be 2.472. This can be verified in Minitab or StatCrunch. So if we were to interpret this, we are 90% confident that the mean weight of pennies minute after 1982 is between 2.456 and 2.472 grams. Now if we were to compare this to our 99% confidence interval, we see that the margin of error has decreased from 0.012 to 0.008. So as we decrease confidence level, the margin of error will decrease. If we increase the confidence level, the margin of error will increase. Suppose that we obtain a simple random sample of pennies minute after 1982. Construct a 99% confidence interval with n equal 35. Assume that the larger sample size results in the same population mean, 2.464. The standard deviation is still sigma equals 0.02. Comment on the effect increasing the sample size has on the width of the interval. We're doing a 99%. Our z alpha over 2 is 2.575. Our lower bound becomes 2.455 because now we're using sample size at 35, and our upper bound becomes 2.473. Again, we can verify this by using StatCrunch or Minitab. To interpret this, we would say we are 99% confident that the population mean weight of pennies minute after 1982 is between 2.455 and 2.473 grams. So as we increased our sample size, our margin of error decreased. So therefore we have a more narrow confidence interval for a sample size. So in the real world, as you increase the sample size, your confidence interval gets smaller, more narrow, and that's good. But at the same time, a bigger sample size means more money and more time. So that's the trade-off. So MOE. MOE is another way to abbreviate margin of error. When the confidence level increases, the margin of error increases. When the sample size increases, the margin of error decreases. Thanks for watching.